Hello and welcome to this video where we're going to be looking at the atomic structure booklet. Again, what I suggest is download the booklet, the link's in the description below, have a go at the questions and then come back here, check yours against our answers and watch through how to answer these exam questions. So let's get started. Okay, so we're going to be looking at the atomic structure booklet today. And let's go through the questions. Okay, so question 1. This question is about nuclear radiation. D and E are different radioactive isotopes. D has a different half-life to E. Explain what's meant by the term half-life for 2 marks. Again, this is a really common exam question. It's just learning those definitions. So the half-life definition you need to know is that it's the time taken, which will get you 1 mark, for the number of nuclei to halve. 2nd mark. Okay, next question. The graph shows how the activity of isotope D and E change with time. Which isotope has the longest half-life? And explain your answer. Well, looking at the graph, we can see that E is the one that has the longest half-life. And this is because it takes a lot longer for the decay. You can see if we take any point, for example, this time here, that D has a lot lower activity than E. So our answer would be E, as it has the activity highest for the longest time. Okay, question 1.3. The table shows some information about different elements. Tellurium-130 is a radioactive isotope. Tellurium-130 decays, emitting a beta particle. Write a balanced nuclear equation for tellurium-130 decay. So, how are we going to do this? Well, number 1, we know it starts with tellurium. We know that its mass number is 130. You don't get a periodic table in the physics exam, that's why they give you the information here. And we can see that the atomic number, weird spelling mistake there, the atomic number for tellurium is 52. So we can put our proton number down here. Now it tells us that it's beta decay, and beta decay releases an electron, which is, electrons have a mass number of 0 and the charge of -1. Once we've done this, we can fill in the numbers. Remember, whatever is the total on this side is the total on this side. So our mass number at the top here must be 130, as 130 plus 0 gives us the 130 here. At the bottom here, we know that 52 is the sum of these 2 numbers here. So this must be 53, because 53 add -1 gives us 52. We then need to refer back to the table to work out which element this is. So the proton number here is 53, which belongs to iodine, has the symbol I. So there we go for our nuclear equation. Finally, in the question, the table shows us how the activity of iodine-131 decreases with time. Calculate the half-life of iodine-131. Now in these questions, you've got to know what to look out for. What I'm looking for is points where the numbers are halving. So if I look here and here, this is really useful because 3.2 halved is 1.6 and halved again is 0.8. So we can see that there have been 2 half-lives, 1, 2. So 1 half-life and 2 half-lives. Now we know this one, 3.2, took place at 4 days. And we know this one here took place in 20 days. So 2 half-lives took the difference between 4 and 20 days, which is 16 days. Therefore, 1 half-life will take half of this side over here, which is 8. So the answer is 8 days. Okay, moving on to question number 2. Question number 2, again, shows us parts of the periodic table, because we won't be given one in our exam. It asks us to work out that yttrium-93 can undergo radioactive decay to form zirconium-93. State the type of radioactive decay that yttrium-93 undergoes. Well, we can see here that the mass doesn't change. So therefore it can't be alpha decay. So we know it's going to be using beta decay, which releases an electron and therefore doesn't change their overall mass. This then helps us to answer the following question, write a nuclear equation for this decay, because again, we can use the information that we know. This is beta decay. which is going to release an electron. At the start here, we're starting off with yttrium. We can see the symbol for yttrium because it's given to us here. We've got the mass number at the top, which is 93, and we've got the proton number over in the table again, which is 39. Again, like last question, we're going to use the fact that the sums of the opposite sides add up. So this would be 40, as 40 plus minus 1 gives us 39. And the mass number at the top will be 93, because 93 plus the 0 leaves us with 93. Finally, we just need to find out what type of atom it's going to produce. Again, we've worked out the proton number, which is 40, and 40 is zirconium, and we can check that because it tells us in the question. Cesium-112 decays by emitting a single particle to form iodine-108. Explain the changes in the cesium nucleus for this decay. The important thing to notice here is that the mass goes from 112 to 108. So the mass is changing by 4. This tells us that it must be alpha decay. It must be releasing a helium nuclei. So to pick up our marks, we talk about the fact that it must be an alpha particle being released, which is 2 protons and 2 neutrons, to explain the changes in the cesium nucleus for this decay. So it's 2 protons and 2 neutrons down. Just move it up there, sorry. Using the figure above in your answer to 2.3, calculate the atomic number of iodine. Well, we know that it's gone from 1112 cesium, which is Cs, to iodine like so. We know that it's released an alpha particle with the 4 and the 2. So we know at the top here, it's going to be 108. We don't need to worry about the atomic number because we do need to know about the atomic number, sorry, because it is asking us for the atomic number. So we know that cesium has an atomic number of 55, and this is reduced by 2, so this will be 53. So therefore we know the atomic number of iodine is 53. The part of the periodic table in the figure above doesn't give a value for the mass number of each element, suggests why this is not usually possible. The atomic number is important, that's the number of protons, and that's always the same for each type of element, whereas the mass number can change due to isotopes. So we would say different isotopes exist, and therefore there is not a fixed mass number for each atom in the periodic table. Okay, moving on to question 3. So this is talking about an X-ray image. You can see the X-ray image here. And it says that small fractures sometimes don't show up on an X-ray. And so to see these fractures, doctors will inject the patient with a radioactive isotope. The image is formed by detecting the radiation as it leaves the body. The figure below shows an image of a foot after the patient was injected with the radioactive isotope technetium-99. Technetium-99 emits gamma radiation. What is gamma radiation? Well, the first thing we need to say about gamma radiation is that it's electromagnetic radiation. However, this isn't usually enough for the 1 mark. We want to state where that radiation has come from. So it's electromagnetic radiation that's been released from the nucleus. To explain why gamma emitter is used. A gamma emitter is used, or gamma radiation is used, because gamma is more penetrating. Due to this, it will be able to exit from inside the body through the skin, whereas other forms of radiation like beta or alpha might have got stopped. So gamma is more penetrating, so more will leave the body and easy to detect on the outside. Technetium-99 has a half-life of 6 hours. Give the meaning of the term half-life. Again, it's only a 1 marker. We need to get both those points in that we said earlier. So it's the time taken for the number of nuclei of a radioactive isotope to halve. Again, learning those, use our knowledge builders, nice and simple. After treatment, hospital equipment may become contaminated. Describe the level of hazard associated with contamination with technetium-99. You should include in your answer a description of how the hazard level changes over time. Well, this is all to do with our half-life graphs. And the idea, the half-life decay looks something like this. So we get really rapid decay at the start, followed by much less decay at much lower levels at the end. So initially, there will be a high level of hazard, because initially right at the start here we're at our highest level, and then we can say that that level will quickly drop, as in this exponential decay, it's much faster dropping at the start than it is at the end. And this is mainly due to the short half-life of the tracer that they'll use. Some of the equipment may also be irradiated during treatment. Describe how treatment becomes irradiated. Well, to irradiate something, you literally expose it to ionizing radiation. Why is irradiated equipment not hazardous? The reason it's not hazardous is it's exposed to the ionizing radiation, but it doesn't become radioactive itself. So the equipment doesn't become radioactive. Okay, moving on. Here we've got a label of the subatomic particles on the diagram, which represents an atom of lithium. So around about the outside, we've got our electrons in the shells. When we come to the nucleus, we need to decide which is which. So you can see we know we've got the protons and the neutrons, we need to decide which. So over here, we've got the atomic number, which is 3, which is the number of protons. And you can see that the filled in pink circles here are 3 of them, so that's our protons. And then the 1, 2, 3, 4 remaining clear circles must be our neutrons. Which type of particle found inside the atom is uncharged? Well, uncharged will be the neutron. Neutral, no charge. What's the mass number of this atom? Well, there's 2 reasons we can work this out. It actually gives it to us up here, which is 7. Alternatively, if they don't do that, you can just count the number of protons and neutrons inside the nucleus. So we've got 1, 2, 3, 4, 5, 6, 7. Obviously, it's quite easy when there's 7. If there's lots of them, putting a little dot in them just reminds you which one you've counted. So the mass number is 7, and give a reason for your answer. Well, that is the total number of protons and neutrons. Okay, the diagram below represents 3 atoms, X, Y, and Z. Which of the 2 atoms are from the same element? Give a reason for your answer. Well, we know atoms of the same element have the same number of protons. Our protons are filled in circles. So if we count the number of filled in circles here, we've got 1, 2, 3, 4, 5, 6, 7 protons. Over here we've got 1, 2, 3, 4, 5, 6 protons. And here we've got 1, 2, 3, 4, 5, 6 protons. So therefore we know that Y and Z must be from the same atom. And the reason being they've got the same number of protons. And finally 4.5, in the early part of the 20th century, scientists investigate the paths taken by positively charged alpha particles into and out of a very thin piece of gold foil. The diagram shows the paths of those 3 alpha particles. Explain the different paths A, B and C of the alpha particles. If we look at A, in A they've passed straight through. And that's because that's the empty area of an atom, and so they can pass straight through that empty space. In B, you can see that they've started to be deflected or repelled, and that's because we've got the positive charge here of the nucleus repelling the positive charge of the alpha particles. So deflected or repelled by the positively charged nucleus. And C, you can see that that repulsion has happened completely to reflect them back. So they've been repelled back in the direction they came. It's important in these questions not to refer to them hitting the nucleus. They don't hit the nucleus, they're repelled by those like charges. Okay, moving on. Again, this is a really common, simple question that comes up, which is to fill in this table, or sometimes it's, they give you bits of the table to fill in those missing parts. So the relative mass of a proton is 1, of a neutron is also 1. An electron is so small that we refer to the mass as negligible. The relative charge of a proton is +1, remembering to give the plus. A neutron is 0, it has no charge. An electron has a charge of -1. In the next question, it's all about potassium. It tells us potassium is a metallic element in group 1. It tells us it has an atomic number of 19. It tells us its most common isotope and another isotope that we get. State the number of protons, neutrons, and electrons in potassium-39. So we're going to be using this bit here. So the number of protons, that number at the bottom is 19. The mass number at the top here, 39, is the number of protons plus the number of neutrons. We know that the number of protons is 19, so the number of neutrons, therefore, must be 20. 19 plus 20 gives us 39. And the number of electrons in the atom will be the same as the number of protons, so that would also be 19. Explain why potassium-40 has a different mass number from potassium-39. Well, potassium-40 is an isotope, and isotopes have different numbers of neutrons, whereas this one has 20. Potassium-40 would have 21. 21 plus the 19 getting us to the 40. Technetium is produced by the radioactive decay of molybdenum. What changes occur in the nucleus of a molybdenum atom when this happens? Okay, so if we're looking here, you can see we've gone from 9943 to 9942. So the changes at the top here is 0. Change at the bottom here is 1. Oh, I've gone the wrong way around because I've read it in the question incorrectly, so actually it should be like this. And that's where you can see picking up your answers. So that's a negative charge because it's an electron that's being released. And so we know therefore that it is beta decay. And so it asks us specifically for what changes occur in the nucleus of a molybdenum atom when this occurs. Well, therefore we know that a neutron has turned into a proton, releasing an electron. Describe the structure of an alpha particle. Well, an alpha particle is the same as a helium nuclei, which means it has 2 protons and 2 neutrons, and we can draw it like this. 2 for the number of protons, 4 for the mass number in an alpha particle. What are beta particles? Beta particles are fast-moving electrons. Describe how beta radiation is produced by a radioactive isotope. So again, got a very similar answer to above. So a neutron turns into a proton in the nucleus, which releases an electron, which is our beta particle. Okay, let's keep going with all these questions. Lots of questions there to do. Okay, so this diagram shows a method of controlling the thickness of paper produced at a paper mill. A radioactive source which emits beta radiation is placed on one side of the paper, and a radiation detector is placed on the other. How the amount of radiation reaching the detector change as the paper gets thicker? Well, as the paper gets thicker, it's going to do a better job of blocking the radiation, so the amount of radiation will decrease. So the amount of radiation will decrease as paper thickness increases. Explain as fully as you can why a radioactive source which emits alpha radiation couldn't be used for this application. Well, the reason there is that the alpha radiation would be blocked by the paper and wouldn't be detected. So it wouldn't be able to get through, and you wouldn't be able to tell whether the paper is thick or thin because any paper thickness would block it. Why a radioactive source which emits gamma radiation couldn't be used for this? It's kind of the opposite answer. So gamma radiation is very penetrating and no thickness of paper would block it. So it wouldn't matter if the paper was thick or thin, it just wouldn't get through. Why a radioactive source which emits beta radiation can be used? Again, so it's in that middle thing, the middle of the two answers before. So beta radiation would decrease at the detector as the thickness of the paper increases. Americium-241 is a radioactive isotope used in smoke detectors. There's a proton number of 95 and a mass number of 241. The half-life of Americium-241 is 433 years. How long would it take for the Americium-241 in a smoke detector to go to 1/8 of its original number of radioactive atoms? So if we think about it firstly being at 1, after one half-life, it would go to a half. After a second half-life, it would go to a quarter. And after a third half-life, it would go to an 1/8. So it's going to take us 3 half-lives. We know that each half-life is 433 years long. So if we do 3 times 433, we're going to get to 1,299 years. Okay, next questions. When an atom of thorium-232 decays and an alpha particle is emitted from the nucleus, an atom of radium is left behind. Complete the equation for this decay. So it told us it's an alpha particle being emitted, so we can put our alpha particle, which is 4 to alpha. And again, remember our numbers at the top add up, so we know this one will be 228. That's 228 plus 4 gives us 232. And at the bottom it will be 88. 88 plus 2 is 90. We need to put the element symbol. The element symbol is radium, Ra. It tells us in the question in the periodic table. It then tells us that radium decays by emitting a beta particle from the nucleus. So again, we know it's a beta particle, so a beta particle will be 0 and -1. And again, we can do the same trick with the numbers. So at the top there will be 228. 228 plus 0 gives us 228. And at the bottom will be 89. 89 plus -1 gives us 88. And we know it's actinium, so we can put our AC in like so. Okay, next question. These graphs look a little bit tricky at first, but once you know how to read them, once you practice these questions, it becomes a lot easier. So it tells us that thorium eventually decays to the stable isotope of lead-208. All the steps can be shown in this diagram. Nucleons, this word here, which we haven't met before, is the number of protons and neutrons in an atom. So we've got to work out what decay is happening between each of these stages. So if we look for the decay between A and B, we can see that we're going from here with approximately just over 230, say 232 nucleons, to B, which is just over here, which I reckon is around about 228. So you can see we've lost 4 nucleons. So if we've lost 4 nucleons, that means we're losing an alpha particle, and so therefore we know that this is an alpha particle. If we look at B to C, you can see here that the number of nucleons has stayed the same. It hasn't changed, but the number of protons has gone up from 88 to 89. Well, that's telling us that this must be beta decay, and where the neutron has released the electron, turning into a proton, so the proton number has changed and moved up, but the number of the number of nucleons in total hasn't. If we're looking for the decay from E to F is here, and again you can see it's that position where we're losing 4 nucleons. It's an alpha particle, and the decay from I to J over here, again, is the same as B to C. It's a beta particle. No change in the number of nucleons, but an increase of 1 in the number of protons. Okay, let's have a quick look at our next page. Atoms are very small, and most of their mass is concentrated in the nucleus. Electrons orbit at different distances from the nucleus, and the nucleus is much smaller than an atom. Approximately how many times smaller is a nucleus than an atom? The answer is 10,000. Again, it's one of those questions straight from the spec that you need to learn. The increase in an atom can only orbit at the electrons in an atom can only orbit at specific distances from the nucleus. State what causes an electron's distance from the nucleus to increase or decrease. So for an electron's distance in orbit to increase, therefore it needs an increase in energy, so it must have absorbed some electromagnetic radiation. For it to decrease, it's the opposite. So it's going to emit electromagnetic radiation. Atoms have different atomic numbers and mass numbers. In terms of subatomic particles, describe the difference between an atom's atomic number and its mass number. So here we really need to define what those two things are. So the atomic number is the number of protons. So we're referring to our subatomic particle there. And our mass number is the total number of protons and neutrons. Nice and easy with our definitions. Okay, don't get put off in this next question by the word transmutation. Again, it's telling you what it is. It's the name given to a process where one element can change into another. Explain and compare how two different types of radioactive decay can cause transmutation. Well, the two different types of radioactive decay that cause transmutation are the ones that change the number of protons, and that's therefore our alpha decay and our beta decay. So in alpha decay, we release an alpha particle, and releasing an alpha particle causes the atomic number to decrease by 2, because you're releasing 2 protons as part of that helium nuclei. Beta releases an electron, which occurs when a neutron decays into a proton, and therefore the atomic number will increase by 1 because you're producing a proton. Okay, in our next question, the figure shows the reactivity of a radioactive isotope changing over an 8-hour period. Predict how long it will take for the count rate to fall from 100 to 1.56 becquerels. So if we work out first of all how many half-lives we're looking at, so if we start off with 100, half of 100 is 50, and 25, it's going to test my maths, 12.5, 6.25, 3.125, and 1.56125 or so. So we can see that to get to 1.56, it's 1 half-life, 2, 3, 4, 5, 6 half-lives. We then need to use the graph to work out how long each half-life is. So it starts at 100, better with a ruler, but we go along 50 and down. You can see that 1 half-life equals 2 hours. So 6 half-lives, each of 2 hours, gives us 12 hours. Okay, in question 11, alpha, beta and gamma are types of nuclear radiation. The teacher sets up a demonstration of the penetration properties of alpha, beta and gamma. So they've got the different types of radiation. You can see where they're getting blocked. Complete the figure by writing the name of the radiation in each block. So alpha is our least penetrating, gets stopped by the paper. This must be our alpha. Beta is the second most penetrating, and the most penetrating is gamma, which you can see passes through the paper, passes through the aluminium, and is passing through the lead there. Okay, give 2 safety precautions, and again, really important to know the safety precautions with any of these practicals that a teacher should take in a demonstration. So there's loads and loads here, we only need 2, so don't point the sources at people. So students or demonstrators is a really important one. Use tongs to handle the radioactive sources would be another good answer. You could have lots of things though, only keep them out for as long as you need them, not using gloves, keeping the sources away from your body, etc. Plenty of different activities you could get. Okay, continue on that question of 11. A table below shows how the count rate of a radioactive source changes with time. Describe the relationship shown in the table. Again, it's 2 marks, so we need to do more than just state the simplest fact. So the simplest one is that as time increases, you can see the time increases here, the count rate decreases. Okay, so it's going to pick you up your first mark. And again, like all of these things, use what's in the box, use the titles, it makes it a lot easier. So we're looking at a radioactive source, so we could maybe look for a pattern. We're thinking about half-life, and if it starts at 600, you can see it then goes to 300. So in 80 seconds, it's halved. We can see that again. It's another 80 seconds takes us to 150, which is half of 300. So our second mark is it halves every 80 seconds. So use the table above to predict the count rate after 200 seconds. So after 200 seconds, the easiest way I think about this is we know that at 120 seconds, the count rate was 221. So after 200 seconds, that's one half-life, that's 80 seconds there. So we know that this number here should have halved. So half of 221 is going to be 110.5. So let's round that up to 111 seconds. The half-life of the radioactive source is very short. Give one reason why the source would be much less hazardous after 800 seconds. And again, this is like that question before. It's to do with the fact that the fall is very, very rapid quickly. So therefore, it will be much less hazardous because there will be a very small output of radioactivity after 800 seconds, probably much closer to the background rate. Okay, the graph below shows how the count rate from a sample containing radioactive substance cobalt-60 changes with time. What's the half-life of cobalt-60? Again, so it starts at 200, half of 200 is 100, we're going to go across. Obviously you'd be using a ruler for this, and down, and you can see that we nicely land on 5 years. Remember to show your working, because if you get something wrong here, you might pick up marks on the working column. And finally, our last page here. So Dr. Franklin shows a class an experiment. She uses 3 different radioactive sources, alpha, beta, and gamma. She uses different thicknesses of paper, so we can see that here, the different thicknesses of paper between the source and the sensor, and she measures the nuclear radiation from each source using the sensor. It only emits one type of radiation for each source, so X, Y, and Z, and they could be alpha, beta, or gamma. And let's see if we can work out what they are. So it's a nice, easy 6-mark question in terms of the structure of the question, because it's 6 marks, so we're going to get 1 mark each for identifying it, each source correctly, and then for our reason. So let's have a look at X. So if we look at X, there seems to be no difference. They're all roughly around about 30. So that tells us that the paper wasn't blocking any of the radiation, so it must be almost penetrating. So X is going to be gamma, and the reason being that the reading always around 30, therefore not being blocked. Let's have a look at Y, where you can see that Y very quickly goes down, and by the time we've got to 0.8 millimeters of thickness, it's barely registering anything, probably some background radiation, so it must be our one that's getting blocked the easiest. So this would be alpha, blocked by 0.8 millimeter thick paper. Now don't fall into the trap, it doesn't necessarily mean it could be beta next, but let's have a look. So we can see that it is quite high, and we can see that it's going down as it's going through here. So source Z would be beta, and the reason being it did change with the thickness. So it went down with thickness, but could still pass through. Okay, so there we go. That was our questions on atomic structure. So have a look through, see how you did, and good luck with your exams. Happy sciencing!